Welcome back to the concrete design series. In this presentation, we will cover how to calculate the quantity of materials required to make up a concrete mix for a particular design. We will also go through the relationship between the water-cement ratio and concrete strength, durability, as well as the concrete slump value. Okay, here we have a stiffened raft slab on ground, and the compressive strength to be adopted for that particular design is F-C is 20 MPa. Now, the aim of this example is to determine the following. Number one, I'll put it in 4 different questions, okay? The first question is, determine the maximum allowable water-cement ratio to be used in the mix. So in this case here, we need to check compliance with the required concrete strength, durability, which is the workability, durability and workability. And slump is the workability. So here we basically select the worst case scenario that would give us the lowest water-cement ratio. The second question is determine the quantity of the materials required to make up the concrete mix ratio of 1 to 4. Okay, so that is 1 part cement, and we will allow 20% fly ash within this 1 part of cement. 2 parts sand, and call that the fine aggregate with 4% moisture content, and 4 parts coarse aggregate, the larger aggregates, and that has 2% moisture content. The quantity of each material is to be documented in kilogram per meter cube, and of course water will be in liters. The third question is determine the maximum amount of water that needs to be added to the mix after consideration of moisture content, right, in the aggregates, and provide the final batch quantity per meter cubed. And the final one, which is the exciting one, determine the batch quantity required to make up the concrete mix for the entire slab on ground in kilogram. With the final question, once you know the entire batch, we can work out the cost, we can work out the total dead weight, and it gets exciting from there. So here we have a stiffened raft slab, which is 16 meters long, 8 meters wide, and 2 edge beams along with 3 internal beams, okay, in that longer direction. And in here we have 2 edge beams with 1 internal beam in the shorter direction, in that 8 meter direction. Now the edge and internal beams dimensions are shown here, but we will thoroughly go through it in the fourth question. Also, with the reinforcements, I have not shown it here just for clarity, so we can focus on the concrete material quantity only. The other thing that is generally a stiffened raft slab is slightly tapered. If you look it up in some textbooks and the code, the Australian footing code AS 2870, you'll find that it's slightly tapered. However, in this case, we will just assume it to be straight, a straight edge beam, for simplicity when we calculate the volume towards the end of the presentation. Okay, now what design information has been given to us? Let's have a look. Number 1, allow 20% fly ash as admixture in the cement. Moisture content of the fine aggregate, which is sand, we can allow 4%, and the moisture content in the coarse aggregate is 2%. Exposure classification is A1, and I got that from AS 3600 2018, clause 4.1 and table 4.10.3.2. Okay, that's the exposure of the slab, the site exposure. Okay. The environment description of that exposure is mild. So everything is indoor and there's no moisture exposure. In this particular example, we don't have an alfresco or an exposed outdoor alfresco. Everything is covered. Okay. We will use the normal density concrete of 2400 kilogram per meter cube, and that is the wet state. So this is including the moisture. Everything adds up to 2400 kilogram per meter cube. And finally, initially we will allow a slump of 100 millimeters. Okay, now let's address the first question. Number 1, determine the maximum allowable water cement ratio to be used in the mix. All right. Again, like I said before, we need to check compliance with the required concrete strength, durability, and workability. The first step, check the maximum water cement ratio to maintain the minimum compressive stress of 20 MPa. As a rule of thumb, according to many concrete design handbooks and textbooks, you'll find that for 20 MPa, the water cement ratio is approximately 0.6 to 0.65. You really do not want to exceed that. You don't want to exceed 0.6. But if you're within that range, I think you're good to go. So you could refer to many standards and textbooks. It will give you information about that. Step 2, check the maximum water cement ratio to maintain the chosen slump or the workability for 100 millimeters. It is important to note that slump is dependent on many things, okay? The aggregate size and shape, use of admixture like plasticizers or super plasticizers, temperature, and mixing time as well. That makes a difference, and the method involved. So with the water cement ratio, it is a major factor, and a slump must always be verified through trial mixes and slump testing on site. You can refer, if you're in Australia here, you can refer to AS 1012.3.1. Now there is an empirical equation which is really helpful for estimation. I think it's conservative in basic mixes, right? It is a linear approximation. Sometimes it's used, I use it most of the time, and it gives me a fairly conservative value. The equation is the slump in millimeters is equal to 550 multiplied by, open a bracket, water cement ratio, okay, minus 200. Please verify this equation in your textbooks if you can. It is difficult to find, but so in this case, we've adopted a slump of 100 millimeters. Therefore, the maximum water cement ratio for that chosen slump is equal to 100 plus 200 divided by 550. And we will get water cement ratio of 0.55. Step 3, check the maximum water cement ratio for durability as per AS 3600-2018. We said before that the exposure classification is A1, all right? And the environment description is mild. So from the tables, you can look it up in the code, you will find that the water cement ratio is 0.65 for durability. Now step 4 is select the maximum water cement ratio for the design. When we say maximum, you want the minimum value, the smallest value, okay? Now from the previous steps, the smallest one was water cement ratio of 0.55, okay? So so that's the governing factor to maintain a slump of 100 millimeters. So we need to make sure that we don't exceed 0.55. Okay, that's it for the first question. Let's move on to the second one. Determine the quantity of materials required to make up the concrete mix ratio of 1 to 4. So that is basically, it's like 1 part cement with 20% fly ash. So within this one part, there will be 80% cement and 20% fly ash. And then we'll have 2 parts sand, that's the fine aggregate with the 4% moisture, and 4 part aggregates, okay? And again, that's the coarse aggregate with 2% moisture. The quantity of the material is, again, to be documented as kilogram per meter cube, and that's generally the density. Okay, step 1. The first step is really express these masses in terms of one part, and we will call that C. So the number 1 in that one part, we can call that C. So let C be mass corresponding to one part in that ratio of 1:4. All right, before the fly ash split, before we include the fly ash. So that means the cement, the actual cement will be 0.8 times C. And then the fly ash will be 0.2 C. Okay, so 0.2 and 0.8 will give us the 1. All right, you with me? And then the sand will be 2C, that's the second ratio. And then the coarse aggregate will be 4C. The water in this case will be 0.55 multiplied by the ratio of the cement, which is 0.8 times cement, the actual cement. In this example, we will look at the water cement ratio only. I won't add the fly ash to it. You can say the water to the paste ratio, but for the sake of this example, we will just look at the water to cement ratio. All right, so water then will end up being 0.44 C. The total wet mass, which includes the water, will be 0.8 C plus 0.2 C, which is, so 0.8 C is the cement, 0.2 C is the fly ash, and then 2 C is the sand, and 4 C is the coarse aggregate, and then 0.44 C is the water. If we add all of this up, it will be 7.44 C. Now, set the total mass. We have then 2,400, that's the density, 2,400 kilogram per meter cube. So we divide 2,400 divided by 7.44. Therefore, we will get C is equal to 322.58 kilogram per meter cubed. All right, step 2, the dry component masses. Now, cement, we said it was 0.8 C, okay? And that will give us 0.8 times 322.58, if you remember, we worked that out. So that will give us 258.06 kilogram per meter cubed. The fly ash is 0.2 C, 64.52. Sand is 2 C, 645.16. And then the coarse aggregate is 4 C, which is 1290.32. Now in this table here, the sand and the aggregates does not include the moisture, okay? Does not include the moisture. The entire water in the cement, in the mix, is 0.55 multiplied by the cement, which is 141.94 liters, okay? So again, if you note here, we've only allowed the water to cement ratio. So that's the entire amount of water that we can allow in the mix, to include any moisture as well. So water cannot exceed 141.94. All right. Step 3, convert to wet mass to whey. Okay, so we need to adjust now the moisture, have the moisture correction. How do we do that? Wet mass to whey is equal to the dry mass divided by 1 minus the moisture fraction. All right. So what materials do we have that are wet? We have sand, which has 4% moisture, and the coarse aggregate, which has 2% moisture. So sand, the dry mass is 645.16. With 4% moisture, we will end up getting 672 0.04 kilogram per meter cube. All right. So for example, here I put it down here as sand wet weight is 645.16 divided by 1 minus 0.04, because 4 divided by 100 is 0.04. That will give us 672.04 kilogram per meter cube. Now, if you take this 672.04 and subtract it from the initial dry weight, which is 645.16, you will get 26.88 liters. All right, and we do the same with the coarse aggregate. Okay, so in this case, we will have the dry weight, which is 1290.32 divided by 1 minus 0.02 is equal to 1316.65 kilogram per meter cube. Then the water in the coarse aggregate is 1316.65 minus 1290.32 will give us 26.33 liters. All right. So yeah. Okay, guys. We might just end the video here and continue question 3 and 4 in the next video, part 2. Now, if you've been enjoying this and you're finding it useful, please share, like, and subscribe so that others may also learn. See you in the next video, and until next time, we hope that you have a great afternoon.